instruction. So it's sort of like here. We have an add here. This is the target, and here is the source. Okay, so this $0 gets its correct value after the 5th clock cycle. But for the second instruction, at the first, second, third, fourth, at the 4th clock cycle, the second instruction needs to get the value of $S0. So it's still the old value. So how to do that? We do the data forwarding, which means that, in fact, after the 3rd clock cycle, we have already computed T0 plus T1. We already get the value, but we haven't put the value to S0 yet. But we have the value. So we forward that value as the input of EX. So conceptually, it's sort of like we forward the output here to here. But internal wirely, it's if we really draw a wire, this output has to wire back to the input here. Right, so at the next clock cycle, it can be the input of the output of the previous instruction could be the input of the next instruction. Okay, does that make sense? Let me say that again. So the T0 plus T1, the value is already available after the 3rd clock cycle, but it hasn't been put into S0 yet. So instead of reading the input from S0, we read the input from the output of the ALU directly. So that's called data forwarding. So let's look at, now we have continuous R-type instructions, right? So we have a sub, an AND, an OR, an add, and store word. So the output of this ALU is forwarded to as the first input of the ALU of the next instruction. Okay. Likewise, this R-type instruction, it also need to read something from $2. But if we didn't do the data forwarding, we need the $2 at the 5th clock cycle. So again, this $2 is available only after the clock cycle 5. So we do another forwarding here. We need another forwarding. Right, so we forward the second input of this ALU is in fact forwarded from here to here. So at the beginning of the clock cycle 5, $2 is still not updated. But $1 plus $3 is available. So we simply forward the sum from here to here. Okay. All right. And from the next one, the next instruction, we also need to have the $2. But now the $2 has already have the right value. So at this moment, we don't need to do the data forwarding. We just retrieve $2 from the register directly, because the register is the right value. Okay, the next one again, at the store word, this $2 is the right value, so we don't need to do the data forwarding. We just read it from the register directly. Okay. So at the 5th clock cycle, if $1 plus $3 is in fact -20, so let's look at the value in $2. So in the first 4 clock cycles, they are still the old value. And at the 5th clock cycle, initially it's still the old value. But then it is updated to the right value. And from then on, they are the right value. Okay? So now let's check what other things we need to do inside the CPU design. So this is the original pipeline without data forwarding. We said without data forwarding, we have 5 stages. Right? We have the instruction fetch, instruction decode, execution, memory access, and write back. Now we have the data forwarding, which means that sometimes we need to forward the data from the output of the ALU back to the input. Sometimes we need to forward the data from this stage, the 4th stage, back here. Okay, so we need to, not only that, we also need to detect whether there's a data hazard or not. So when will we have a data hazard? If we have continuous R-type instructions, and let's say we have 2 consecutive R-type instructions, and if the destination of the first instruction is the source of the second instruction, there will be a data hazard. Right? If we have 2 consecutive R-type instructions, and for the destination of the first one is the source of the second one, there will be a data hazard. Or if we have 3 consecutive instructions, the first one and the third one are R-type, and the destination of the first one is the source of the third one, there will still be a data hazard. Okay, so we have to check these situations. Okay, so we have a forwarding unit. What are the input of this forwarding unit? We need to check the RD field, the destination field. Now let's take a look at the data hazard caused by R-type instruction first. Okay, so for R-type instruction, the write register is always RD. So here we have to check whether your previous instruction, the RD field in your previous instruction, is the same as the RS or RT in your previous in your later instruction. Okay, so let's say we have an add $1 $2 $3 at. Okay, so the at $1, $2, $3 is at its 4th stage, and if okay, so if the destination of the previous instruction is the same as the RS or RT of the next instruction, there will be a data hazard, right? So that's why this forwarding unit has to receive the RS or RT field in the new instruction and the RD field in the previous instruction. If they are the same, there will be a hazard. Not only that, if this add instruction is here, which means this add instruction is 2 instructions earlier than this instruction, there will still be a hazard. So you also need to check whether the RD in whether the RD in the last 2 instructions here is the same as the RS or RT in the current instruction. Does that make sense? Because for R-type instruction, you need to check, for consecutive R-type instruction, you need to check not only the neighboring instruction, you also need to check the neighbor's neighbor. Okay? So if this RD, the RD of this instruction is the same as RS or RT here, there will be a data hazard. That's case 1. Case 2 is if the RD here is the same as the RS or RT here, there will be a data hazard. Okay? So this forwarding unit need to take not only the RS and RT at this stage, but also the RD at this stage and the RD at this stage. Okay, so that's why we have two RD input here and RS and RT inputs here. All right, so that's how we detect a data hazard. All right, so let's see. This is sort of just like the thing I described, except that it's written down. If the RD in the previous instruction is the same as the RS or RT in the current instruction, there will be data hazard. That's case number 1A and 1B. Case 2A and 2B are if the previous the previous and previous RD is the same as the current RS or RT, there will also be a hazard. So in the case of 1A and 1B, we need to forward the summation from execution to memory pipeline. Let's see. Let me check if that's correct. All right, that's correct. So if that's the 1A or 1B case, that's the neighboring, the previous write, the previous RD equals to the next RS or RT. Then in that case, we need to forward the sum from the execution and memory register to the input of the ALU. If that's case 2A or 2B, we need to forward the sum from memory and write back state register back to the input of ALU. Okay. Okay, and here is just that we only forward the instruction if we indeed need to write something to the register. If that's not the right instruction, then of course that doesn't need to do it. And only if the RD is not 0. If RD is 0, then because 0 it cannot be written. Right, so we don't need to really do the forwarding. Okay, so let's see. So you need this forwarding unit. We have already said that it need to take the RS and RT here, and the RD here, and the RD here. And it need to control the input of the ALU, whether that's come from the RS field or from previous sums. Okay, so check these marks. It's 3 inputs. One is from the RS field. This one is from RS. This one is from, let me check. Okay, so it's from the summation of the previous instruction. Okay, and this input here is from the sum of the previous instruction. Okay, so if this forwarding unit found that the current RS is the previous RD, it will enable this line. Okay, because this is the sum of the previous instruction. if this forwarding unit found that the RS equals to the RD of the previous instruction, then it enables this line, because this line connects to the output of the previous instruction here, previous instruction. Where is it? Let me follow it again. Here, from here to here to here. Oh, it's here. Sorry, it's here. This is the output of previous sum. All right, and how about this one? Again, this is from either RT or from, let's check, from the previous instruction, the output of the previous instruction, or from the output of the previous instruction. Right? So if this forwarding unit found that RT equals to the RD of the previous instruction, then this input will be passed here. If this forwarding unit found that the RT equals to the RD of the previous instruction, then this input will be passed here. Okay, so the control signal of these two muxes is decided by this forwarding unit. It detects which kind of data hazard is happening, and then set the control signal to the proper values, and then the right things will be passed as the input of these ALUs. Okay? Does that make sense? All right. So if you write everything in the pseudocode, some people find that it's easier to process. So let me write it in pseudocode. So it says that, let me check it. If the previous RD equals to a current RS, and not only that, if we really want to write something to register, and also the RD is not 0, then the forward A is 10, which means this one is 10. The control signal here is 10. So which means this one will be passed here. Okay. If let's see, if the previous RD equals to the current RT, then that is your previous RD is your current RT. This line will be passed. Okay, so this control signal has to be 10 so that this line will be passed. All right. Now let's call the execution hazard. Execution hazard is you have two consecutive instructions, and your previous RD is your next RT or RS. This is called memory. What is memory hazard? Memory hazard is your previous RD is your current RS or RT. Okay, so if your previous RD is your current RS, and you indeed want to write something to register, and your RD is not 0, then your forward A is 0, 1, which means this line, this data will be passed here. Okay, and the last case is if your previous RD is your current RT, then this line will be passed. Okay, so that's the pseudocode here. All right, so that's the data hazard related to R-type instructions. Next week, I will talk about the data hazard related to load instructions. And we will also talk about control hazard. And that's all. Perhaps if we still have time, we will probably have a quick review about what might be included in the midterm exam. Okay?